So let's review our discussion from lecture on the heating and cooling of buildings. This is section 3.3 of the textbook. The first equation here, this differential equation, is what we produced to describe the rate of change of the temperature inside of a building, which will be represented as capital T of little t, where little t is time. And its derivative with respect to time is given by these components here on the right-hand side. According to Newton's law of cooling, the rate of change will be proportional to this difference between the outside temperature, represented as m of t, and the inside temperature, which is capital T of t. So we take the difference of those two quantities as a function of time and multiply by this proportionality constant k. That constant k usually depends on physical properties such as doors, windows, insulation, and things like that. Then additive terms could be heat due to people, lights, or machines. That would be represented as a function h of t. And then, of course, if you have a furnace or air conditioning, you would add that on as utility, and that would be represented as u of t. So think of h of t for human-generated heat, u of t as utilities. Then, as we did in the class, if you write this equation in standard form that we've seen before for linear differential equations, you would have k being the equivalent to p of t, and your q of t would be all those other terms that we had earlier. Again, after putting it in standard form. The solution, after finding the integration constant, which is e to the kt, would take on this particular form you see here. And keep in mind the integration constant is inside this bracket, so e to the minus kt is multiplied by not only this integral, but also times that constant. And so whatever scenario you want to look at, you'll be defining what these functions m, h, and u are, and then you'll have to do the appropriate integration. All right. So let's review the first scenario that we talked about in class. So let me scoot this over a little bit. And the first particular scenario we had in class is that we were looking at a case in which the outside temperature, so we'll call this scenario 1, or example 1. In scenario 1, what we had is that the outside temperature remains constant. So the outside temp is constant, and we'll represent that as m0. And another consideration for this particular problem, we'll assume that the h of t term, heat due to people, lights, machinery, is non-existent, so we'll assume that h of t is identically 0. And we'll also assume that we have no air conditioning or furnace involved, and so that term will be 0. So let's go ahead and, again, the outside temperature, what we're saying is assuming that initially it's equal to m0 and it stays constant. So if we plug that information into our equation, and I guess I should say that it's not only initially, it's always m0, so that's what it means to be constant. So the outside temperature never changes. So the m of t is just that fixed constant. So then if we go back to our solution, the form of our solution, we'll just rewrite it again. We know that the model of temperature change inside the building takes on this particular form. Integral to kt, quantity k, m of t, plus h of t, plus u of t, close that off, integrating with respect to time, dt, plus that constant, close the bracket. So for this particular problem, we're just going to use the information given to us. This term right here will be exactly 0 because we're not taking into account any heat due to people, lights, machinery, anything like that. We have no air conditioning. That term will be 0. And we've already decided that this outside temperature remains constant, which is m0. Right? So what the problem then turns out to reduce to is that the model of temperature inside the building, in this case, becomes e to the kt times the integral of e to the kt, k times a constant m0 dt plus the constant. Okay. And of course, that's all just simply going to be, if we do the integration, we're going to have minus kt, then we're integrating with respect to t. So what we will get inside that bracket is just m0 times e to the kt. Because fortunately, if the exponent here is kt, we'll have k dt sitting right there for us. So that integral will be very simply that form, add the constant. And then you could multiply through that term right there. And what you would have is that t of t is just simply m0 plus c times e to the minus kt. Okay. And of course, we would, if we had some initial temperature for inside the building, and let's assume we do, because we could remove this constant. We can actually determine it if we have an initial condition. So let's assume we have an initial condition right here. Let's assume that the initial condition we have is that initially the temperature inside the building is this value T0. So therefore T0, which is what you would get when you plug in 0 in for time, according to the equation above, will be m0 plus c times e to the minus k, quantity 0 there. That would then say that T0, push this up a little bit, is equal to m0 plus c times, this of course will be e to the 0 power, or what that says is that T0 minus m0 is equal to the constant. So the constant is the difference between the outside temperature initially and the inside temperature initially. So the overall model we have then for this particular problem is that the temperature inside the building is your initial outside temperature plus the difference in the inside and outside times e to the minus k, and you'll have this term t minus t0. Just after you represent what c is. Okay. And as indicated in class, what happens in the limit of this temperature function as t goes to infinity, if we assume that the initial outside temperature is less than the indoor temperature, you're adding a positive quantity times this exponential form, but of course in the limit this t will go to infinity, but this is e to the minus constant k, which we'll assume is positive. And so what will happen is this term will eventually go to 0. So in the limit, what you would have is that this quantity would be simply the outside temperature. So ultimately, without any air conditioning, no effect of humid heating due to the humans, and with a constant outside temperature, your indoor temperature is eventually going to become the same as your outside temperature. Now, an interesting question to ask, and this relates to one of your homework problems, is let's look at determining, so let's write this as a question we're interested in. How can we determine how much time it will take for the building temperature to change significantly? It's a natural question to ask. in modeling these kinds of heating and cooling situations. So how much time does it really take for the temperature to change significantly? What we do in this case is consider the case of a linear differential equation of the following form. So we'll look at one that looks like this. Suppose we're looking at an arbitrary quantity a with respect to time, assuming it's a function t. So this function of t, all right, its derivative, suppose it has this form, minus alpha a. Okay. So you can so quickly it's easy to determine that the solution for this kind of a differential equation just has the form that a of t would have to be, let's say, a0 if we had an initial condition, alpha e to the alpha t. All right. So this is just a very standard solution, very easy to determine, separable equation there. And notice here that what happens to this function, a of t, just given this exponential form? We can see that it's either going to decay exponentially. It's going to go to 0, so it'll decay exponentially. For the case, or let's just say if alpha is greater than 0, because then this will be e to the minus positive alpha t, so it'll be 1 over e to the alpha t, right? But also know that a of t would grow exponentially. So it'll decay if the alpha term is, the alpha constant there is positive. But if the alpha was negative, of course, then this would be e to a positive power times t, and of course that would grow exponentially. Right? So notice if we looked at, what could you say about what the value of the quantity a would be if we evaluated at 1 over alpha? This term actually on the right-hand side, the negative alpha a, we're going to say, well, if you actually plugged in 1 over alpha into that function, to the solution to the differential equation, mind you, what would you have? You would have a of 0 times e to the minus alpha, and you would plug in 1 over alpha here. But of course, that's just going to simply be a of 0 times e to the minus 1 power, which is a of 0 over e. Right? So what we've actually stated here is that 1 over alpha, a of 1 over alpha, is equal to the initial value of how much quantity you had in A divided by E. So we could say, interpreting this, that it takes one over alpha time to change A of t from its initial value, A of 0, to A of 0 divided by E. So it's a reduction in the original amount that you had. It would take 1 over alpha time. So this is an example of if alpha is strictly positive, the solution is going to decay exponentially, but we'll know in 1 over alpha time it's dropped by this amount. Okay? So we can then adapt this to the particular problem that we were just looking at, and look at it in this particular form, where if we go back to the example we had earlier, slide this over, okay? Well, let's just move it up a little bit. So the other problem we had, of course, is a differential equation where the temperature inside the building is being modeled and could be represented according to Newton's law of cooling, minus K T plus K times M0, right? It's another way of writing what we had earlier, okay? And of course, we could write it as minus k times the quantity T minus M, 0. Because again, for the problem, the scenario we were just solving for, we assume that the outside temperature is constant. So outside temp constant means that M of T is always going to be this M0 value, all right? And again, we assumed U of T is 0 and H of T is 0. So that's the model we had. But notice that if the derivative of T with respect to time is equal to minus K times this particular right-hand side, okay, this is what we have, it is also true that the derivative of T as a function of time minus M0, a constant with respect to time, would also be that minus K times T of T minus 0. Now why is that true? Well, because the derivative of that constant is 0 as well. So these two statements are actually equivalent. But what's interesting now is we actually have this in that form of the linear differential equation we had earlier, where we said if it was in this form, this minus alpha times A, we knew that it took 1 over alpha time to get to A0 of E. Right? So for this particular problem, the alpha is K. So what we have is that 1 over K is the time it takes for the interior temperature, T of T, to change from, in this case, the initial temperature will be T0 minus M0, again, because this A of T now is this T of T minus a constant. So initially your inside temperature is T0, so it'll change from this to T0 minus M0 over E. And that 1 over K value has a particular name. 1 over K is called a time constant. That is your time constant for the differential equation. So it's 1 over K when you can write the differential equation of this form, that it is written in this particular form that you're taking the representation of the function here and you have that same function represented here with just minus K in front of it. Typical values for 1 over K in the heating and cooling arena is usually typically 2 to 4 hours it takes to get a significant change in temperature. You think of the cycle of days, of a daily temperature change inside your house. That's when you would notice the most difference, somewhere between 2 to 4. But the value of the time constant for the differential equation is called 1 over K.